Hello everyone, thanks for tuning in. My name is Andrea Cordaro and today I'm going to talk about inverse design metagratings for far-field integral equation solving. This is a collaboration between the group of Albert Pohlmann at AMOF, the group of Nederenghet at Penn, and Andrea Lu at ASRC CUNY. The idea of using an analog platform to solve integral equations has been recently demonstrated by the group of Engeta in the microwaves in this pioneering work at the bottom left here. So an integral equation is an equation involving an unknown function, here g of u, and integrals of that function that has to be solved for g of u. If the limits of integration are fixed, then we're talking about a Fredholm equation. If the unknown function appears inside and outside the integral, then it's an equation of the second kind. So here what we have is a Fredholm equation of the second kind. The function k of two variables is called kernel, and I of u is a known extra function. When I of u is equal to 0, the equation is said homogeneous. To solve this integral equation, we first discretize the variables and we turn it into a matrix equation. So the variables u and v become vectors with elements in the range a to b, so those are the limits of integration, and the kernel thus becomes an n by n matrix. The analogy with this analog machine on the left is that we also define discrete ports, in this case physical waveguides, and we have a metamaterial that we can optimize whose scattering matrix acts as a discretized kernel. In this case we call it ST. Now we still have to solve this matrix equation. The way we want to do this is by successive approximations. So we start with an initial guess g of 0 and we take it equal to I of u. So the choice here is not mandatory, and it's equivalent to saying that the term of the equation containing the integral is small relative to I of u. Next we plug our first guess g of 0 again into our matrix equation to obtain a more refined guess. We call it g of 1. Now if we repeat the procedure, we can obtain an even more refined guess. We call it g of 2, and you can see here that we're starting building up a series. So this actually is called Neumann series, and it's a generalization of the geometric series for operators. The solution G is the sum of the series, and it's the inverse of the identity matrix minus the scattering matrix. So basically this system computes the inverse of a matrix in an analog fashion. Now this discussion so far is based on three ingredients. So we first discretize the problem, and in this case this would be equal to having discrete ports, in this case physical waveguides. Next, we needed a metamaterial that we can design whose scattering matrix acts as a discretized kernel. And finally, for the Neumann series, we actually need a feedback system. So in this cartoon here, the waveguides are looped back into the metamaterial. Now here we want to design a similar system for free space radiation and indivisible. So we need the same three ingredients. So first, we want to map the physical ports into diffraction orders of a metagrating. The second ingredient is that we want to design the kernel by shaping the unit cell of the grating. And finally, we want to provide feedback with a semi-transparent mirror placed in reflection. So let's start with the first ingredient. We want to define the ports, so the diffraction channels, and we choose a 2D cross grating with periodicities P and W, such that we have only 3 diffraction orders in the superstrate, which is silica, and 5 in the substrate, that is sapphire. Let's label these diffraction channels as ports in the scattering matrix formalism, where the column index indicates the source channel and the row indicates the output channels. Now we have port 1 to 3 in reflection and port 4 to 6 in transmission. Now we need to optimize only the reflection block of the scattering matrix, so that's the portion highlighted in red, because the Neumann series is performed in reflection, so on ports 1, 2 and 3. To simplify the notation, let's call the reflection block of the scattering matrix simply S1R. Okay, now the question is, can we design a metasurface given a desired scattering matrix? To do that, we use a joint method-based topology optimization, and we end up with this weird shape in the unit cell here, plotted in the middle. That it's discretized between silicon and silica. The figure of merit is the sum of distances on the complex plane between the desired S parameters and the optimized one. So in the plot to the right, you can see 1 point on the complex plane for each S matrix elements. So you can see here that actually the match is quite good between the desired and the optimized scattering matrix. Now the last ingredient is the feedback system and the matrix inversion. So let's add the mirror and we follow the path of light to see how we get the Neumann series in such a case. So the transmission block of the scattering matrix of the entire stack, including the mirror, is composed by a sum of terms. The first term is light transmitted through the mirror and the metasurface, okay, where MT in this formula here is the mirror transmission. Now we also have light that is reflected by the metasurface and the mirror and then transmitted. So that's the second term appearing here, and so on and so forth. So for multiple passes. So we end up with a Neumann series, and you can see here that the final formula is actually that the transmission of the total stack is proportional to the metasurface transmission times the inverse of the identity matrix minus the mirror reflection times the metasurface reflection, and finally times the mirror transmission. So as a last thing, we want to check this formula in simulation. So we want to compare the simulated transmission of the entire stack, including the mirror. So again, S2 of t down there. To the right side of the formula, there is actually the analytical Neumann series. So we want to check if the equality holds by calculating the two sides of the equation separately. Now, as you can see again in the complex plane from the plots, the match is actually quite good. And this proves that in simulation we can invert the kernel that we have designed. So to sum up, we showed how to design the scattering matrix and how to invert it with a feedback system. Now the next step is the experiment. So we fabricated the structure experimentally by e-beam lithography on silicon and sapphire substrate. The fabricated unit cell matches the desired one quite closely, as you can see in the SEM image of the unit cell here on the right. Next, we measure the transmittance of the fabricated metasurfaces. So basically normal incidence to zero order diffraction. So in our S matrix formalism, this would be the absolute square value of the element 5,2, as you can see in the label in the plot here. And this also shows a good agreement with the simulation. The next step in fabrication is then to planarize the metagrating to have a flat surface for the mirror. So to do that, we spin a silicon solid gel that we can then anneal. And as you can see in the fib cross-section, we were not able to detect any air inclusion, so the top surface also looks good and rather smooth. Finally, the last step is to evaporate the semi-transparent mirror. So we use 15 nanometers of gold on 2 nanometers of titanium as an addition layer. And we measure again the transmission, again showing a good match between simulation and experiment. So to conclude, also in experiment, we can prove that we can design and invert a desired scattering matrix and thus solve the corresponding discretized integral equation. And with that, I would like to thank you and conclude my talk. Thank you.